We can begin. So this is the beginning of the JCEP seminar series. So this is the first of 6 Friday seminars given at in the same format. For those of you who are not aware, the Joint Center for Extreme Photonics, or JCEP, is a joint research center between the National Research Council, NRC, and the University of Ottawa. And its goal is to advance research in areas of quantum optics, systems in intense fields, and molecular systems. So NRC contributes real money to this center, which is used to hire grad students and postdocs. And this funding really cements the partnership and the relationship between the two organizations, and in my opinion is essential to a successful joint center. So today our speakers are Khabat Hashemi from NRC and Ibrahim Karimi from Ottawa. And Khabat is going to start. So take it away, Khabat.
Thank you, David. I'm just gonna share my screen. Please let me know if you can see the slides and hear me.
Yep, I can see your slide and I can hear you. And no, you want a laser, not a pen, I think.
Okay.
There you
go. Thank you very much. Just a quick introduction for myself. For those of you who don't know me, my name is Khabat. I'm a research officer at the National Research Council of Canada, but also adjunct at the Department of Physics at the University of Ottawa, and a fellow at NRC Ottawa Joint Center for Extreme Photonics. So today I will be talking mostly about the collaborative work that's being done as part of the JCEP in collaboration with the University of Ottawa. The talk is it's going to be a smooth transition between part 1 and part 2. So I'll give mostly an introductory part about our vision, and then talk about some of the results we have, and then Ibrahim will continue with more recent outcomes of this collaboration. Okay. So believe it or not, this photo was taken end of January this year. This is the JCEP inauguration at the ARC building. We will not be able to take photos like this for a long time, I guess. So NRC in Ottawa, as David described, initiated the Joint Center for Extreme Photonics. If you look up NRC's publications in sort of platforms like Scopus, Ottawa is our sort of largest contributor and collaborator in terms of the number of joint publications among any other institutions. So obviously it makes sense to invest in focus areas such as quantum photonics and out-of-second science, and the combination that we all like to call extreme photonics. And on the right, this is a snapshot of the website Extreme Photonics, which will gradually be populated with our research news and other related topics. So just a brief outlook of the talk. I'll talk about just an introduction generally on quantum information processing and its benefits, and then we'll share a vision on how to approach a quantum network at a global scale, and then focus on our collaborative work on free space, high-dimensional quantum communication, and also some recent results on quantum communication in noisy environments. So generally, in the past 30, 40 years, we started to learn, or even longer, 50 years, we started to learn how to apply principles of quantum physics to information processing. And this resulted in three fundamental implications involving that we can show that there's a concrete benefit to use quantum states, quantum devices to do sensing and metrology in communication and also computation. There are clear benefits in these three areas. Just to briefly mention, there are examples. For example, if you use quantum states of light, particularly squeezed states, for example, you can have an enhancement in precision, for example, in an interferometric measurement, and this is part of the plan at LIGO that does gravitational sensing, and the probe light is going to be upgraded to a squeeze light to achieve an enhancement in terms of sensitivity. That's just one example. There are ideas, for example, how to connect different atomic ensembles that can be used as clocks and have a global clock, or on the other hand, have a more precise clock per number of atoms used. There are plenty of ideas in quantum sensing, but that's not our focus for today, so I'll just show these examples. In terms of quantum computation, there are various platforms. Here, just an example of trapped ions, superconducting circuits, which is now popular with Google and IBM, and also photonic circuits. There are two big startups focused on this approach. And then the spin-based quantum computation, which this is one of the approaches that's now being pursued at NRC, and then various other groups around the world. I'm not going to talk about the details of quantum computation again, because the quantum communication side is our focus. So on quantum communication, the goal or the improvement we expect from using quantum states is security and standard encryption. The security always relies on an assumption, which is a mathematical problem is difficult to solve using existing computers. But quantum computing is now, there are ideas that shows that we can solve those problems more efficiently on quantum computers. That generates a threat basically to the encryption infrastructure that's being used today. On the other hand, if you try to use the quantum states of photons for communication, and then that means that if you, for example, encode information in the polarization of the photons, or timing or frequency, or the spatial structure, such as the orbital angular momentum, you can have, I'm calling this unconditional security, but it has conditions on the sender and the receiver. Assuming that those are secured inside a building, then you don't have to make any assumptions about computational power of the eavesdropper or the security of the channel. So how this works is usually the sender sends a photon. So we usually call it Alice. Alice sends a photon to Bob, and she encodes the information in 1 degree of freedom of the photon. You can choose any degree of freedom. This can also be done with photon pair sources, when you have a correlated pair and you encode information in sort of the pair, and then you share that pair between the two parties. I'll talk about this in a bit in more detail, but this has its own. So there are demonstrations, for example, in the city of Calgary, there's a network of a few kilometers of one link with an 11-kilometer fiber. But if the goal is to reach thousands of kilometers to have a quantum internet at the scale of the conventional internet, there are problems to address. Mainly, for example, if we use fiber, there's the minimum loss that are known to us is this 0.15 dB per kilometer, even though that's a small amount. But if you try to just do the scenario that I described here, is if I want to send a photon across a 2,000 kilometer fiber, and repeat this at the gigahertz rate. So every nanosecond, if I try this again, it will take more than the age of universe to get one photon successfully from one end of the fiber to the other. And this is just because of the exponential loss in the fiber. So obviously this is a significant barrier. In the classical or conventional internet, what we do is that every 50 or 100 kilometers, there's a repeater station that reads the signal, amplifies it, and sends it forward. In quantum communication, we cannot do that because the communication security is based on the fact that we cannot copy or amplify a signal without adding noise to it. This is in conflict with the main principle that gives us the security. So we have to find clever ways to send quantum signals over long distances, and there are various ways that I'll talk about. One is, which is becoming now, it's a very complex operation, but multiple groups and countries are now approaching this, including Canada, is to use satellites. And the reason is that the loss through the free space, either from the ground to the satellite or to satellite to the ground, is not exponential anymore. And that would allow us to create sort of links over long distances. For example, this project in China, the satellite is called Misius, achieved entanglement distribution and quantum communication over 1,200 kilometers. The vision that we like to focus on is to have a Canada-wide quantum network. Given the scale of Canada, if we figure out every detail of this sort of platform, it would be applicable to global scales as well, because Canada is a big country, about 4,000 kilometers from east to west. And so this vision, I'll try to convince you it will require every technology we know of, both in terms of fiber-based and free space and satellites to make it work. And then we are working towards different elements of this vision. So in terms of links, there are various ways, and each are optimal in a certain regime. For example, direct ground-based links. That means that using a fiber, not doing anything clever, just like fiber without any devices in the middle. It has been shown that you can go up to 400, 500 kilometers, and then after that, you'll have to give up some security assumption, for example, for quantum key distribution, in order to go to over longer distances. There's an example of this. It's called a trusted node. It's a relay scheme in China that extends to about 2,000 kilometers. Low Earth orbit satellites covers about 1,000 to 5,000 kilometers. Geostationary or below Earth orbit satellites cover about 5,000 to 14,000 kilometers, but you can see that there's no overlap between these things, so it probably means that all of these are required to go to the global scales. But also there are more clever things that we know how to do, but they are complex, so it requires work and research for its development. And then one is, for example, quantum repeaters, and that means that we need quantum some operations and quantum storage in order to distributed entanglement, for example, over about 500 to 2,000 kilometers. And there are other approaches that I'm not going to talk about, but also a combination of something that we came up with. It's a combination of quantum repeaters and low Earth orbit satellites. This would take you to the 20,000 kilometer, which is basically end to end. This is the longest distance one would want to go on Earth. So these are different approaches, but the focus of the rest of the talk today is on free space links, and also Ibrahim will talk about a couple of examples for underwater quantum communication. Just a list of, not complete list, but a list of possible applications of such a network. Quantum key distribution for secure communication is a standard, obvious one, but also there are ideas along private quantum computing, where you can post your task to a server without allowing the server to know the result of your calculation or even the problem that you try to solve. Better telescopes in the domain of sensing. You can extend baseline of telescopes using shared entanglement. There's a lot of fundamental physics that can be tested using entanglement over long distances. Network of clocks for both correlated clocks and also higher precision, and so on, and also interconnecting both at the laboratory scale or longer distances, interconnecting quantum computing devices. These are all applications of such a network. In this talk, we'll just focus on QKD. So what we do use is high dimensionality. So the standard approach that I'll describe briefly is using just polarization, but we're using spatial structure of the light to give us higher dimensionality, and there's some benefit to that I'll talk about. So different components that would go into a quantum communication system is as a source. There are various types, and they all have different security implications. Energy channel could be free space, fiber, underwater, and we talk about, I think Ibrahim will talk about both free space and underwater, and then also encoding, which would be which degree of freedom, for example, is going to be used. And so there's a depiction of that I'll talk about. So it described the orbital angular momentum states briefly. And also detection schemes. So there are various detection approaches. But on top of all these things, there's also the recipe or the protocol that we use to establish that secure communication was performed. So I'll talk about both the states, high dimensionality and its benefit, and also some of the protocols that we try to explore using this flexible system. So these are just an example of orbital angular momentum states in terms of the dimensionality. As soon as you choose, for example, this is at L = 3, it gives you 7 states. This is not enough for quantum, excuse me, for quantum key distribution. We always need a conjugate space, and in this case, these are just an example or depiction of those states that can be used. And the high dimensionality gives us a larger alphabet set to encode information, and therefore per attempt we can encode more information per photon. This is just shows that the overlap of these states are 1/7, which is 1 over the dimensionality of the Hilbert space. Just an example of the kind of probably the most famous quantum key distribution protocol. It's the BB84. It was invented by Bennett and Brassard in year 1984. So the idea is that Alice chooses a basis in terms of polarization that could be HV polarization or A and D, as the conjugate basis. So it's a random selection of polarization basis, and then we assign 0, for example, to horizontal and 1 to vertical, and then in the other basis we 0 to diagonal and anti-diagonal, and 1 to anti-diagonal. And that becomes the basis of our encoding. So if she wants to share a 0 in this basis, she sends a horizontally polarized photon. So then Bob chooses also randomly without discussing at this stage a basis for the measurement, and then Alice sends the photon. Bob's measure the photons, and then they classically pick up the phone and they try to discuss the measurement basis, not the measurement results, just the basis. They throw out the measurement operations that did not match the preparation stage, and then keep the ones that randomly match, and then just repeat this process for a long time. As a result, they end up with a random sequence of 0s and 1s that is secure and it's shared between them, but it's not accessible to an outsider. This is not the message that's being transported. It's it's just the key that you can later use to encode, to encrypt a message. So it's important to know that distinction. So one thing that I like to highlight is the difference between, or the impact of the dimensionality. This is not exactly related to quantum communication, but this paper sort of highlighted how a system in dimension 2, or a certain combination of a state in a system in dimension 2 cannot be replicated in a different dimensionality or different Hilbert space. So that probably makes the point that in quantum mechanics, as opposed to the classical version, that you can go from a basis of just binary from 0 and 1 to a basis 10. They can all be identical. In quantum mechanics, that's not true. We don't exactly use this type of states or principle, but just to make the point that a high dimensionality can make a difference. So the way that this is just shows that how the key rate per photon changes as a function of error in the system, and it can be shown that there's proof that we can tolerate for the scheme that I described, the BB84 scheme. When you use polarization or just a two-dimensional Hilbert space, you can tolerate up to 11% noise. This changes when we increase the dimensionality to 4. It goes up to about 18-19%, and so on. So we are going to use this increased noise tolerance and also increased information capacity as a resource. So this was shown in this. This is just Ibrahim will talk about this more in more detail. And then this is the goal that we're going to work towards. So going from a 300-meter link to a 5.5-kilometer link between NRC and Montreal Road campus and U Ottawa campus. So the flexibility of this orbital angular, like the preparation and detection of orbital angular momentum states, allowed us to explore various protocols and see how they perform. We did this in this work. And there's so I'll just refer you to the paper. One thing that I like to highlight is this specific scheme. It's called round robin differential phase shift, where the encoding of 0s and 1s or 0 and pi is just the phase difference between different modes. And this was proposed and done in time. As you can see, there's a pulse train in time. But we used orbital angular momentum states to do this, and the platform became a lot simpler than what you see here. And in this experiment, these were experiments required a lot of resources in terms of number of detectors or number of stabilized interferometers. But instead, we replaced that with 2 SLMs, and it showed that we can also do round-robin differential phase shift quantum communication, quantum key distribution using orbital angular momentum states. Just to so touch on a recent result, this vision requires also, it's not just sort of linking free space links and fiber links. It requires a lot of components because sometimes sort of propagated, photons compatible with fiber are not necessarily compatible with the free space links or the satellite links. So there's a lot of components needed to make something like this work. There's a whole, again, incomplete list here. One thing that I like to focus is the qubit conversion. This was done, it started a couple of years ago and recently resulted in this recent result that allows us to do quantum communication in noisy environments. Just to, running out of time, just to quickly give you a summary, the goal here, so if we try to convert, for example, information that's encoded in time, which is, photons being early pulse or late pulse, what people always did was to send us, just passively send us through a delayed interferometer and throw away half of the pulse and then convert the initial state with a 50% probability to a polarization encoded state. This is not efficient, and we thought if we can actively switch the polarization of one of these photons, we would be able to do this with 100% efficiency. So this was the motivation, and this early work, we showed that the polarization switching can be done with fairly good efficiencies approaching 100%. And then later, this was initially done in a YAG crystal. Later, this was shown in a single mode fiber, that this polarization switching can be done in a fiber. Therefore, it allows to do more efficient switching and also in an integrated way, ideally. So this was used in this idea that if you want to send in a quantum key distribution scheme, if you want to send a single photon from Alice to Bob, but if there's a very bright source generating noise, for example, in a satellite quantum communication, if you want to operate at daytime, there could be a lot of noise coming from sunlight. Or in fiber-based quantum communication, for example, if you don't use a dark fiber, if you use an existing fiber that's being used for the telecommunication network, it means that there will be a lot of background noise. So it would be useful to figure out a way to operate in noisy environments. The idea here is that this is just to show the effect in time and in frequency. And then the idea here is that with the switch, we can actively choose a very well-defined temporal window and get rid of all the noise in different time bins and only select the signal that's coming at a very specific time. This can be done on top of passive just spectral filtering by just adding a filter to the setup. And we showed that this arrangement with the active temporal filtering and the spectral filtering would allow us to pick out the signal that was initially overwhelmed with noise. This is just showing that, again, this was done in a single mode fiber with pretty high switching efficiency. But the more interesting slide is this one that shows a significant improvement, about 3 orders of magnitude improvement, when we use this ultra-fast temporal filtering as a switch. So the noise tolerance, which means that that's the point that the quantum key distribution system fails and then the key rate collapses to 0. That noise tolerance can go up by about a factor of 2,000, which is a very significant improvement compared to not doing anything and just hoping for a noiseless environment. for the operation. So these are just various ways of showing the same improvement, basically. Just to highlight is that an IP was provisionally filed this week, and the paper is under review, submitted, and it's under review at the moment. I should highlight that our RA, Fred Bouchard, he did he did a significant amount of work pushing this idea and bring it to fruition. To finish, I'd like to sort of mention that how our work interfaced with a challenge program at NRC. There's a challenge program. It's called High Throughput and Secure Networks, or the short is HTSN. It's directed by Sylvain Raymond. A proposal was submitted, led by the University of Ottawa, by Ibrahim and Jeff Landine, and collaborators from U of A, and also NRC collaborators, our team, and we hope to increase the collaborators from add collaborators from U of C and UK. This resulted in investment in a joint lab, which is very well in line with the spirit of the JCEP. So we're very excited to be part of this. The other sort of hopeful note is that both Ibrahim and myself and a few other people involved in JCEP are collaborators in an attempt to prepare an NFRF transformation proposal for development of a quantum network, quantum internet in Canada. So with that, I'm going to hand this over to Ibrahim, and he will talk about more recent results from this collaboration.
So thank you, Chabad. Okay, so do you want to have questions at the end? I don't know. How is the structure, David?
Well, whatever. Do people have urgent questions, or would they prefer to see Ibrahim's take on this? Okay, I don't see any questions. So why don't you start your presentation now, Ibrahim?
Absolutely. Okay. Okay, let me play. Do you have the screen?
Yes, I can see it.
Okay, fantastic. So I will turn off the video and then stop video. Okay, so thank you very much, Chabad, and also thank you for NRC for hosting us today. So this is almost a report, I would say, on the recently launched JCEP, Joint Center for Extreme Photonics. And Chabad and I, we are working on high-dimensional quantum cryptography. And this year, we will talk about what is happening in Ottawa. So I'm based in the University of Ottawa. I'm a kind of researcher in the field of structured light, which soon will be structured quantum waves. So, and I'm a fellow of Max Planck Center for Extreme Quantum Photonics and fellow of a Joint Center for Extreme Photonics, which is NRC Ottawa. Okay, so just briefly mentioning.
Sorry to interrupt you. Can you leave your video on, because I like to see your face when you're explaining all these slides. I can put your.
Okay, just give me a second. Of course, start video. Is that fine?
Yeah.
Let me change the background. I don't want you to be interrupted with the Star Trek. Okay, I will give you a very nice view now. Okay, so let me start with this. Sorry. It's fine? Okay, so Chabad mentioned briefly that why we care about structured photons. I mean, what you use for communication. I mean, rarely happens that someone uses electrons for communication. I mean, in the wires, yes, but in a free space, no, because it interacts with other materials or it interacts with electric and magnetic fields. So we use light because photon rarely happens to interact with other materials. I mean, we see refractive indexes, but the interaction is really minimized compared to other particles that they use. So when you deal with this particle, you have to understand what property this particle has in such a way that you can encode information in those properties. So I use the quantum language. I apologize for that, although many people, they may raise question, photon doesn't have a wave function, but anyway. So when you deal with photons, photon can be labeled with a frequency, can be labeled with polarization, can be labeled with the number of photons, can be labeled with transverse structure modes, which in this case is P and L that you will see here. So I have a little bit of problem with these keynotes. So sorry, remote control, let me see. No, does that allow me? No. Anyway, I remember I had in the past this issue again. So we can deal, we can create a photon which can be in a very complex superposition of all of those degrees of freedom. For example, on the right side of the screen, what you will see that we created a single photon which is in superposition of specific radial mode, specific orbital angular momentum, and specific polarization state. And then again, summing up another specific states. So when you sum them all together, you will deal with a very rich topology or rich structure, which has higher, that gives you the possibility to use the higher dimensionality of information. So in this case, you will create a photon which is, if you look point by point, the polarization is changing and is not uniform. And also the electric field, the magnitude and phase of electric field at those points is changing dramatically. So we call these structured light or structured photons. So we have the ability in our laboratory to manufacture devices that can shape and create these sorts of beams in the laboratory, working in the quantum regime and also in the classical regime. And this is liquid crystal facility that we have. So you can take a piece of glass, which is usually ITO glass, because later on we want to apply electric field to it. And point by point, you will align specific polymer there. So you coat with a polymer, and then you align those polymer with incident line. So you have a UV light that point by point you align these polymers. That what you will end up, pixel by pixel on the right side of the screen, you can orient them in a specific topology. You can take two of them together, we glue them, and the distance between these two pieces of glasses, which the polymer is coated, is about, let's say, a couple of micron. And then we inject liquid crystal between them. And then what we will see, if you place it between two polarizers, you will see some sort of, let's say, birefringent, which is point by point is different. And when you shine light on the top of that, you can create specific modes of light. And if you change the polarization of incident beam, then this structure will change accordingly. So for example, we were able to create, let's say, in-Scotian beam, or we can create lenses, we can create airy beams, which is one of the interests for the people that they do microscopy, or we can, what is our interest is orbital angular momentum. For example, we can create a beam which has orbital angular momentum of 200, which is really huge. It's not a world record, but it's really reasonably high. Okay, so we have these technology in the lab, and when I call Q-plate, I mean these devices, which is a slab of liquid crystal devices. We can apply voltage to it, and also we can control the polarization, and then we will see that the structural light or OM carrying beam will change accordingly. So for example, I'm sure that will be one of the questions that people, they will ask, how fast can you do that? The question is, how fast can I manipulate the polarization? If you can manipulate polarization in a gigahertz regime, then you can create orbiting momentum in a gigahertz regime. I think this aligns exactly with the previous talk by Chabad, and also the work by Fred, that you can manipulate, you can create such a fast switch for polarization. And if you cascade it with a Q plate, then what you will get a fast switch for orbiting momentum. Anyway, so we can create these topologies in the laboratory, and these topologies not only in two-dimensional space, but also can be in three-dimensional space. 2 years ago, we were able to create the first ever polarization knot in space. So this topology is not only in two-dimensional space, but also when it propagates, it forms a three-dimensional topology, which has a specific mathematical representation. Last year, we added another, let's say, degrees of freedom to that, and we were able to not only create a knot topology, but also a topology which has a frame to it. And we use these frames to encode prime numbers. And we develop a protocol similar to RSA protocol, which we believe that even is a little bit harder to be break. And right now we are also working on quantum money and using these frame knots to do topological computations. So we have results, but I prefer to not show this here. Okay. So Chabad mentioned that why we care about this high dimensionality, why we are fighting for this. It has two sides of wins. So one is the secret key rate, which increases by the dimensionality. If you have a dimension 2, you can send 1 bit of information. If you have dimension 4, you can send 2 bits of information. If you have 16 dimension, you can send 4 bits of information, okay? So increasing the dimensionality will give you the possibility to increase the secret key rate. On the other side also, if you have noise, the noise tolerance also will increase. So in the dimension 2, if you have 11% in noise in your system, since we don't know where these noise is coming, we associate all of those noises to Eve, someone that wants to attack your system. When you have 11% of error, we are not able mathematically to establish a positive key. So when we have 11%, we say that the channel is no more secure. However, if you go to dimension 4, although you increase the bit rate, but also you increase the threshold that you have it for the security. So the threshold changes from 11% to 19%. So that is extremely useful for noisy channels. Okay, so Chabad mentioned that in 2017, my team, and also in collaboration with NRC at that time, we did a free space high dimensional quantum key distribution link between 2 buildings at the University of Ottawa, and we were able to send to use the high dimensionality as a benefit to establish a positive secret keys. So here, if I want to simplify, on the top right side corner, we had turbulence. Of course, there were no one attacking to our channel, but the noise comes from turbulence, from detectors, from imperfection, whatever. Any experimentalist knows that nothing is perfect in the laboratory. So sometimes there were a lot of wind, and we had huge turbulence. And what we had about 11% error here. And we were not able to use the dimensional space, which was polarization of the light, to send a positive secret key. However, if we jumped from polarization to what we call it spatial modes, then we were able to send a positive secret key even at 11% of error. So we were able to establish 0.65 beats per shifted photons at that time. So that receives a lot of attention by community, and that was, I think, the starting point between the two institutes, University of Ottawa and NRC, to invest and work extensively in this direction. This work receives a lot of attention by media. I think this is one of the goals of these seminars. One of the interesting comments which I received was from, by the way, you see Chabad on the right side corner, and there were a team of people that they did this experiment. Leader was Alicia Seat, which at that time she was a bachelor student, if I recall well. Frederick Bouchard helped a lot. I mean, I think Fred was Alice at that time. He was in the Demares building sending information to Alicia and Robert Fickler, which Robert was a postdoc at that time, and right now he's a professor in Tampere University in Finland. Hugo is the master of the Q plate, and he was the person that created the Q plate there. And one of the interesting comments that I received from our colleagues is from Ephraim Steinberg. He said, okay, with respect to my friends in Ottawa, they say that it's about the real 5CT condition, but then you open the article and you find out that it was done in Ottawa. So he was accusing that Toronto is warmer than Ottawa. Anyway, so we try to extend our knowledge and also extend the condition to more realistic situations. So what we have done, and the team they have done, they built up a 5.4 kilometer free space link between University of Ottawa and NRC, I think library building M50 in Montreal Road. So of course, when you go to the roof, you are not even allowed to have the optics living, keeping them there. So you have to build up a secure place for them. So Felix Hufnagel, which is right now he's a master student. At that time he was a bachelor student. He designed a very safe, let's say, deck, installing an optical table inside and a shed. In such a way that you can keep the optical elements inside of that. So they built up two sheds, one in NRC in Montreal Road and one in the Colonel Bay roof. So you will see people working there, Azad and Felix, Fred, even I think Chabad, although he's theoretician, he helped a lot, and Alicia. So they went to the roof, they built up the shed, and then they make the hole just for stabilizing the optical tables. Of course, for those people that they deal with security, they know safety and security, they know very well that going to the roof is a little bit dangerous. So you have to be trained, and all of those people, they have been trained by the agency. And then finally, they built up sheds with optical tables inside. And of course, and on the NRC side, it gets a little bit colder. At that time, I was traveling, but I remember the temperature was about -10 degrees. So people, they were working there. I should be, by the way, very careful to not show the left side photo because it's against the safety, by the way. Okay, so then they built up the sheds in the NRC one, and then even if you open up Google Map right now, I show two gray arrows there. If you zoom on these 2 points, you will see Alice and Bob on the two roofs, one in the library in NRC and the other one in Colonel Bay. People, they try to send, to align the beam. Of course, we were very careful with the laser safety because we are not allowed to send beam lines within certain degrees of the horizon. So this is against the rule that is posed by the airport. So what they have done, they try to align the beam, and what they found that even few microradian, if I'm not wrong, of misalignment in the lenses produces a very strange effect, which it took Frederick Bochard, Alicia Seat, and Felix a couple of weeks, maybe a couple of days, just to realize that this is some sort of cylindrical lenses. So that is true that the tilting is a little bit small, let's say macroradian, but what is happening in such a long distance that produces some sort of astigmatism. And what they have seen that if you send OM beams, you will see on the other side Hermite-Gaussian beams. And in addition to that, what they have seen huge turbulence. So we realized that we cannot work with this condition unless we should compensate for the turbulence effect. So for this reason, I want to briefly telling you how you can compensate for the turbulence and what will be the effect of the turbulence. When you send a beam through free space, through air, through water, what is happening? The beam gets distorted by the fluctuation that you have it in the density of the material there. So either if it's air, the density of air is changing. This is one of the reasons that you will see star flickering. So if you look at stars in the sky, you will see that it flicks with a certain frequency. Of course, this is the response of our eyes. The frequency is much higher than what we expect. So what is happening? The beam gets disturbed. So you will get speckle patterns somehow with a certain dimensions. It cannot be bigger than that dimension. And what we have to do, we have to bring this beam, distorted beam, to the beam that we want to send. So if you are sending a Gaussian beam, if you get these speckle patterns, at the end you have to end up with a Gaussian beam. So there is a technique that people, they know very well in astronomy, and they develop that, is adaptive optics system. What you do in real time, you calculate what is the distortion on the beam, and then you will tell to an adaptive system, which is a dynamic system, which is made of small deformable mirrors, to compensate for the effect. So this is the scheme that you will see. That's a beam that is coming from Alice. By the way, this beam is only target. It does not carry any information. So a beam from Alice is coming. It goes to the deformable mirror. But before, let's say, the deformable mirror is totally flat. It goes to beam splitter. And then we have a wavefront sensor. And you have to do fast computations to understand what is the distortion on the beam. And then you will tell to the deformable mirror to place the conjugate of the distortion in such a way that you will flatten the phase. And then as a consequence, what you will see on the other side of the beam splitter, you will see that the beam has been recovered. So this should be done in the fraction of a second, I would say below millisecond. And that is computationally expensive, and also in terms of technology is expensive. And it took the company 1 year to build this adaptive optics system for us. And you will see that Alicia, Felix, and Dilip, they opened the box, which is almost a supercomputer with adaptive optics system inside. And then Alicia, I think she runs the code, and she built up a prototype in the laboratory, and she was able to compensate for that. But unfortunately, we faced this pandemic, and we were not able to go to the roof and check out the system. And also last year, we thought very carefully that the weather condition will not allow you always to go to the laboratory and perform the experiment. Then what we have done, we requested for a scintillometer in such a way that in real time you can control and understand the condition of turbulence without going to the laboratory. And we got funding from the agency that now we can install even 2 scintillometers there, and building up a network which can be, everything can be synchronized and also can be monitored in real time. But again, unfortunately, we were not able to go to laboratory, and we have to wait. So we know very well that 6 months in Ottawa we cannot work in the roof on the roof. So then we were looking for the other excuses. Then we chose carefully what else can we do in order to establish a quantum network. So if you look at Earth, you will see that on the Earth we have 70% water, and we have a lot of devices underwater, like a lot of sensors. We have submarines, we have towfish, which they probe and they will get information and they will share with the surface vehicles, or with the ground base, or even in some cases they will communicate with satellite. So we were interested to go to optical domain. And by the way, the wavelength that people they use right now is a very long wavelength. So for example, in the case of submarine should come to the surface, place an antenna of, let's say, 20 meters on the surface, and then doing the communication with the satellite. So if you look at the transparent window of water, and on the right side we show the Beer's law. If you go with telecom wavelength, you will see that the penetration depth is about 300 micron. If you go to 800 nanometer, you will see about 2 meters. If you go to Heine laser, you will get to 15 meters. If you go to 500 green wavelength, you will go to 75 meters. And if you go to UV beams, UV light, which is 420 nanometers, you can even send light through 230 meters of water, based on the condition that the water does not contain scatter materials. I mean, like minerals and algae and etc. So that triggers us to go to an underwater channel and verifying whether we can send and use high dimensionality for quantum key distribution. So this is a cartoon version of the setup. So people, they created single photons there. They try very hard to push to UV. They were not able to do that because phase matching did not allow them. And on the other side, we had no detectors at the telecom wavelength. So they were able to go to 710 nanometer wavelength, and they send signals through the underwater channel through 2 periscopes, one sending in, one picking up. And we tried to minimize the surface deformation by keeping it in an aquarium region, just to minimize the wave that you have on the surface. And then they tried to send the information and detecting on the other side. So this is the scheme of that's a photo which has been taken in Frederick Boschard's parents' house. And that's Felix that is trying to show to me that he's working and aligning the setup. And at the end, what happened, they start to send information and detect from the other side. By the way, ladder is there just to stabilize the 2 breadboards, is not needed, and also bring the classical channel to the other side. So what we know is that if you send light through water, and what we realized that sending light through the water also causes a dramatic astigmatism in the system. So for example, if you send a classical light, which is these petal beams, on the other side you will see a deformed beam, which is not only tip tilt like a free space regime, but also it contains astigmatism. So it changes the shape as well. This is due to the gradient of the temperature that we have it in a real condition. So when there is a gradient of the temperature, you have eddy currents in the water, and that causes a lot of issues for us. But the good point is that here the turbulence is extremely slow comparing to the case of the free space. So they tried to do it in dimension 2, dimension 3, and dimension 4. They were able to go to the dimension 3 and using the benefit of high dimensionality. However, in dimension 4, without compensation for the turbulence, it was impossible to perform to get a positive secret key rates. So we were bounded by dimension 3 at that time. Then later in 2019, they went to outside. They find a place in Ottawa River, and they rent a cottage there, students there. And what they have done, they try to build up a channel which was a little bit longer than the previous case. We were expecting about 10 meters, but unfortunately we were not able to go into that regime because we had a lot of issues with dust and algae at that time, and since we had a heavy rain at that time before performing the experiment. However, what they were able to do, they were able to establish a standard BB84 protocol, and also they were able to use Shack-Hartman sensor to monitor what's going on with the wavefront deformation there. So they were able to measure that do you have a tip tilt only, or you do have also astigmatism in the system. And very recently, which will be the last experiment that I will show, in the collaboration with NRC and the ocean section, people, they went to NRC, I don't remember the building, which contains many flumes there, and they try to increase the length and monitoring what's going on with the secret key rates. So they try to do standard BB84 protocol and also using the vector modes for the first time. So that's a photo of the setup, which is, I think that side is Bob. Sorry, that side is Alice, the other side is Bob. And also you will see Alicia sitting there and sending UV and green laser both together through the water. And you will see that the green depth, penetration depth is much shorter than the UV one. And you will see the UV goes to a longer distance. By the way, this experiment has not been done in the classical regime. It has been done in the quantum regime. They attenuated the power of the laser to be below one photon per in average in mean value, and they try to send structural light, and the other side they do the polarization tomography as well. And finally, what they got, they were able to go to 30 meters, which is a record, I would say, and they were able to send about 80 kilobits per second. With this, by the way, this paper is on archive, and when we place it on archive, Felix got interviewed by IEEE Spectrum and also by Popular Mechanics, by the way, which you will see the title is very strange, that quantum communication could make US submarines even more deadlier. These are the only things that we don't need at this moment right now with the pandemic. So anyway, it received a lot of attention by media. And right now also we are working with a group in NRC to build up optical communication link for underwater sensors in such a way that you will not go, you will not send people underwater and taking the sensor out and transferring the information and placing them back. So that saves a lot of time and a lot of energy, and of course money for the people that they want to get information about what is going on underwater, like the density of plastics and a lot of other information that is useful for the ocean. In the summary, we try to develop our protocols. Chabad talked about the time being, how the time being protocols can be simplified with using the structural light, and also we are working on producing the frame knot, which can be used for quantum computations. we are also trying to build up protocols and also devices that can be used in noisy environment, is what Chabad talked about. And we tried many different channels. I mean, we did not talk about fibers because it's the most trivial case, but we talked about free space and underwater. And we'll be having a quantum network in Ottawa, and we are planning to have the third node in Hospital of Ottawa, in such a way that we have A, B, C, which Alice, Bob, and Charlie, in such a way that they can share the key, and maybe even we are thinking about establishing a teleportation in the city of Ottawa. The final goal, as Chabad mentioned, is going for quantum internet and building up a system, a secure system in such a way that all of them, they are connected to each other via quantum networks. I would like to thank my team, Alicia Seed, Felix Hufnagel, Frederick Bouchard, Robert Fickler, Eliyahu Cohen, by the way, Felix, Dr. Bouchard and Fickler and other people, they are not anymore member of my team. They have their own research group, or they are working independently, but still we are collaborating. So I should call them anymore collaborators. Kevin also is working on developing electronics for the system, because that requires also classical communication in such a way that all of those systems, they should work together. And finally, to all my collaborators, I did not want to divide them in terms of, let's say, classical optics and electron beams and etc. But I want to point out explicitly Chabad, because Chabad helped a lot. Duncan, for the last 2 experiments, he did fantastic work. Ben as well. Phil, he helped a lot on this side. And also with Anne Broban, we are trying very hard to go into the direction of the quantum money and also new protocols that may be used. As well as Paul Corkum, Bob Boyd, and Gerd Loix, Mars Paget, those colleagues that always, they have insightful comments and also exciting project always, to work always with them. So, and to the agency, this part of the project was funded by U Ottawa and NRC explicitly, plus a portion from Max Planck Institute in Germany. I think I'm done. Okay, so shall we invite Chabad as well?
Yeah, okay, so I will applaud on behalf of everybody.
Thank you.
So now is the time, if people have questions, turn on their video and unmute their microphones and speak up. So I'd like to question your interpretation of the comment of, oh, I didn't have my video on either, of Ephraim Steinberg. I don't agree. I think what he was saying is Ottawa is not a real city.
Okay.
Which may be true. So what is
there was a comment, I think from Rene, if I'm not wrong, right? Mm-hmm. Privately, he wrote to me that eddy current is not for water. It's reserved for electric currents. It is reserved for it. You have in both of them, so they call both of them eddy currents. We know, we are familiar with the eddy current in electromagnetism. But also the water one, they call it eddy current.
Thanks. Yeah, I think I got confused.
Okay. Okay.
So what is the highest spatial mode dimensionality that you've transmitted in free space?
In laboratory or?
Yeah, probably laboratory.
In laboratory, Fred is the right person to answer to this question. Fred, correct me if I'm wrong. I think you tried 64 or 128.
No, we can go up to 100 with the spatial light modulator.
Okay.
And that's over a distance of a few meters?
Yeah, these beams diverges quite a bit, very quickly.
And you need right telescope if you want to send it to longer distance. For example, I think we had a telescope of a lens of almost 1 meter, high quality. Yeah,
50 centimeters in diameter.
50 centimeters. Thank you, Alicia. Yes.
So when you have the higher spatial modes, that means more spatial K vectors, or frequency, spatial frequency, and so you have to collect a wider range of angles. Is that right?
Yeah.
Okay.
So I will pose the question also in a different way. I would say that assuming that we have a specific telescope in our laboratory, okay, or in the free space link. So we have an optical system which is cylindrical symmetry. So how many modes can we send there? What is the optimal? Right? So can we send Gaussian, many of those Gaussian beams, or we should send OM beams? I would say that OM beams will not win. You have to send what we call it the natural mode of the system, which is, my apologies for the technical word, they call it Walsh modes. So you have a cylindrical system and you want to have as many as independent orthogonal modes inside of this cylinder. And these modes are known as a Walsh mode. So the azimuthal side is quantized in terms of L, but also the radial part is quantized. So you have to use both L and P of that mode for doing the communications. So that is the maximum number that you can send it there. And it wins against any other modes that you have it. Because it gives you the Schmidt number that you have for this system.
Okay, and is it easy to create this type of mode?
We did, yes. Fred is laughing because the detection is the main problem. Yes, creation is easy, but the detection is the main challenge. With Fred and his colleague in the last years, they have developed a technique that they can detect it. In 2012, with my colleagues, we developed a technique that you can create them in the laboratory. So Fred and we are a good partner on this.
Okay, so I see some other people have their videos on, like Andre Staude. Does that mean you want to ask a question? Big smile.
I can ask a question. So you have combined now these spatial modes with free link, with a free space link. Both of these things are separately already solved, so it seems like you have two problems. One is the free space link, which is tricky because of perturbations and so on, and turbulences. And then you have the other problem with the being able to collect all these spatial modes and so on. You could have more spatial modes if you had a fiber, for instance, or do I not understand this correct?
Yeah, Chabad, do you want to comment on this?
Yeah, sure. Well, the fiber is a single mode or basic fibers. If you want to go to transfer spatial modes in fiber, you have to go to these like special twisted fibers, and that's not as advanced as just basic telecommunication fibers. If you want to go to high dimensionality in fiber, you would go to either frequency or time to encode more information. And so that's a preferred approach, but that comes with its own difficulties. You have to be able to prepare and measure these states in these specific measurement bases, for example. And the switch kind of that Fred is working on, that goes, it's a step towards that. You would be able to prepare and also process high dimensional states in time at least, but there are ways to also extend that concept to frequency. But the high dimensionality argument stays. It's just what's the best choice. I would say with fiber, it's probably time or frequency. With free space, it could be time, frequency, and spatial mode. And you can use all these degrees of freedom. The thing is, for this big quantum Ethernet vision, you need all of these things to work together. Like there are, for example, if you want to aim for a moving target, you can't really attach a fiber to a car if you aim to securely communicate with a moving object. So you need all of these things to work, basically.
I think you're addressing here multiple problems at the same time, right? One is having the direct link between moving targets or spaceships and satellites, submarines and satellites. And the other one is having this quantum encrypted communication, which most of our communication is in fiber. And so you're telling me that basically these spatial modes, they don't exist for fibers, and or they don't work for fibers. You can't have, so that's just my question.
I don't want to say they don't. They do. There's actually a paper by from Ibrahim's group that they do transfer these modes in fiber. It's just not as widespread and advanced as the telecommunication fiber. That's the only point I was trying to make.
Yeah.
Okay.
So
Phil Bustard has a. Do you have a question, Phil? Not with your microphone.
Can I come?
Yeah, please go ahead, Ibrahim.
Yeah. Sorry for you. So yes, you can even use the normal fibers. I mean, the dark fibers that we have okay, and using the spatial mode to send information, in high dimensional information, not only time being. This is what Chabad tried to mention that. So this system is a linear optics, right? The fiber, if you have even 100 kilometers, is a linear optics because the information that I'm sending is not high power, right? So when you send it through these linear optics, at the end, what you are having a mode which is masked, and this mode is it seems that is a crosstalk between all of the other modes. So it excites the other modes that you have it. So I can decompose it and I can understand what are the coefficients of these expansions term. I will send the different modes inside, like the process tomography, the guys that you do. So you would send different modes. At the end, you will analyze what are the outcome of that. You will understand what is the process of these matrix. Okay? Then you invert it, either at the end or at the beginning. It's completely up to you. And you can use the spatial modes to do the multiplexing there. If you were in the Photonic North last year, Peter Windsor gave a fantastic talk. And he said that this is, again, the problem of people that working also in the classical communication. Is the signal to noise ratio important for us? He showed the formula, a simple formula that you have a multiplexing, you have a logarithmic term, and etc. He showed explicitly that even in the classical communication, people, they are fighting for multiplexing. Why? Because it does not go logarithmically, it goes linearly. So that's the reason that in a simple language is infinity of time being, infinity of spatial modes, infinity of vector modes, and multiply all of them together, you will get infinity power of 3, okay? So of course it is a joke, but what is happening is really going for high dimensionality is a win in any cases for you.
Thank you.
I'll jump in with one. It's not a well-formed question, but Ibrahim, you alluded to the introduction of Charlie in your future plans and possibility of entanglement, sharing, and so on. And I was interested as to whether you would envisage using spatial or polarization there as your, or both as your entanglement sharing method, and what is the state of development of the creation of spatial entanglement in these OAM modes in source development?
So Chabad and I, we were thinking, and of course, this is also in collaboration with Ingwen, another member in NRC. So right now we are trying to develop a high-dimensional teleportation in our laboratory, and we can create hyper-entangled states in laboratory by using just two BBO crystals, which they are rotated by 90 degrees with respect to each other. If you go with these modes, you will get polarization entangled and orbital momentum entangled. And of course, later on, you can do a post-selection and you can use the benefit of, let's say, both polarization and the spatial modes there. Yes, that's the plan that we want to do it in between the two, let's say Alice sharing with Bob and Charlie.
Mm-hmm. And is the, like on the spatial side, what sort of dimensionality has been shown in terms of entanglement among the OAM modes?
Spatial side, let me remember. Gosh, -10 to 10, if I'm not wrong. 21 space.
Okay.
Alicia and Felix and Fred can correct me. Chabad, I don't know.
There's a paper by Vienna where they show 100 by 100 dimensional entanglement, considering both the azimuthal and the radial modes.
Oh, yes.
So you could say
the proceeding of National Academy of Science.
Yeah. There was some issues with the way they measured the modes, but it's on the order of 100. That's the highest. Yeah.
Wow. Okay. Yeah. Okay. Thank you.
But that was classical.
That was an entanglement.
Okay.
Yep.
But it's not. You don't. I think it was a fixed system, right? You won't. You were not able to change the state or change like measurement basis or change the dimensionality of the Hilbert space. It was just fixed.
I see.
That's the small difference. It makes a lot of sort of technical challenges.
Yeah. Okay. Thank you.
Okay, I'd like to step in now and call a halt to the proceedings. The pizza has now arrived in room 233. Get it while it's still hot. So thanks to Khavat and Ibrahim for their first presentation for the JCEP series. And next Friday, Albert Stolo and I and two postdocs will also be presenting, and so we'll send out an invitation next week. Thanks very much to everyone.
Are we Thank you. Are we staying, the JCEP members?
I wasn't planning on it, no.
Okay.
Do you have something you wanted to say, or?
Yes, there were two different slides that Chabad and I will prepared, so.
Yeah, just send them by email.
Okay, I will do that.